which is basically some more test, ratio, root, and comparison test. So kicks off Theorem 8.14, the ratio test. And this is on page 641. Okay, so let me preface this by saying this is one of the more useful tests that we're going to have. We're going to use the ratio test a lot, and you're going to have quite a few problems where that's probably about the only way you can do it. And we'll see as we start to do some examples. But let's still first look at what the test says, and then we'll try to do some examples to illustrate how to use this tool. And again, this is a tool to try to determine if a series converges or diverges. Okay, so let's say we have a series of a sub k's. So if we have this, and again, this is going to be positive terms. So far, everything we've been doing has been relying on the idea that the terms are always positive. We're going to go back and look at possibly not always positive terms in 8.6 on Wednesday. But nonetheless, and let's say we have this, and then we're going to make a limit. And we're going to use r to represent the value of our limit. We're going to let r equal the limit as k goes to infinity. And the limit is going to be of a fraction. So r you can think of as ratio. This is a ratio test, right? So what's the ratio going to be? It's going to be the ratio of successive terms, meaning the k plus 1th term divided by the previous k term. And so we just write that as a sub k plus 1 divided by a sub k. So in the ratio test, you're going to create this limit, and you're going to look at the value of this limit r. And then based on the value of this limit, you're going to try to draw conclusions about whether, the series converges or diverges. So here's the criteria. So 1, if 0 is less than or equal to r, which is less than 1, then the series converges. However, if r is greater than 1, then the series diverges. So the only case that we've left out here is if r is equal to 1, then we don't know. Then the way we say is the test is inconclusive, meaning we can't draw any conclusions based on the test. So basically the way the ratio test works is we are looking at some series and we say, I'm trying to figure out if this converges or diverges. So I construct this limit of the ratio of successive terms. And then if I get a number when I take that limit that's less than 1, I'm able to conclude that the series converges. I don't know what it converges to. Again, that's usually not going to be our concern. Similarly, if the series converges to a number r that's bigger than 1, then I'm able to conclude that the series diverges. If it comes out and I do this and it comes out equal to 1, unfortunately the test has not provided me with any information and I need to use some other test to try to do the problem. Okay, so that's how this works. Now let's see this in action, because setting up this limit can look confusing until you get used to doing it a couple of times. And let's just go right ahead with one of their examples to try to help illustrate what's going on in the book. So this is example 1. And again, they have a few of them. We're going to look at part A. And this is still on page 641. So it states that we should use the ratio test to determine whether the following series converge or not. So in part A, we have a series as k goes from 1 to infinity of 10 to the power of k, so that's an exponential, divided by k factorial. All right, so there's a kind of a new thing for us to look at here that hasn't showed up in our series work so far, and that's the idea that the terms of the series in the formula that expresses them has a factorial in it. So a factorial is going to be important to us because factorial is really a formula that we just use for integers. So that means that I can't have an x factorial here. That means I couldn't think of this as a continuous function because it's not. So that means I can't use the integral test, something like that. We could try to take the limit as k goes to infinity to do the divergence test to see if this diverges. But even that's kind of challenging because we're used to limits being applied to continuous functions, not factorial things. So this is challenging. And this is one of the perfect examples of why the ratio tests ends up being very important for things like this. So if you see a factorial in the problem, again, that's this exclamation here. If you see a factorial in the problem, then that's going to be something that's a strong indicator that we really need to be using something like the ratio test. Okay, so just maybe I need a quick reminder because sometimes people confuse it. Remember n factorial with the exclamation symbol means n times n minus 1 times n minus 2 until you get down to a 1. So for example, 4 factorial is 4 times 3 times 2 times 1. And it's just a number. So in this case, you get 24. So that's the idea of the factorial. Okay, so how do we do this? Well, again, let's just take a second and look at the first few terms to try to get a sense of what's going on. When k is a 1, we have 10 to the 1, which is 10, divided by 1. When k is a 2, this goes up to 10 squared, which is 100, divided by 2 factorial, 2 times 1, which is 2. When k is a 3, we have 1,000 divided by 3 factorial, which is 6. 3 times 2 times 1 is 6. So initially, as we look at the first few terms, the numerator is growing up exponentially. 10, 100, 1,000, 10,000, 100,000, million. Whereas the bottom factorial doesn't seem to be growing as fast. 1, 2, 6, the next term would be 24, things like that. So it may look like the top is growing more than the bottom, and therefore this diverges. Your intuition would probably expect that if you were looking at these first few terms, because they just seem to be getting bigger and bigger and bigger, not getting smaller and smaller. The divergence test says if the terms themselves are not shrinking away to 0 as you go to infinity, that it must diverge. And these first terms are getting larger instead of getting smaller. However, looks can be deceiving. So let's see if we could test this using the ratio test. So what would the ratio test say? So for the ratio test, we would let R equal the limit as k goes to infinity of a fraction. And so to do the k plus 1 term, I basically replace k with k plus 1 in each of its spots. So in the top, I would have 10 to the k plus 1 power divided by k plus 1 factorial. So I basically just took the two k's in the formula for the terms and replaced them with k plus 1. Then in the bottom, I'm supposed to divide by a sub k, which is just this formula right here. So in the bottom, I would have 10 to the k power divided by k factorial. And I have to take the limit of this as k goes to infinity. So this may look very intimidating initially because I have a big fraction with little fractions in it. And it's very common when we are trying to evaluate series that the series shows up like this, like a ratio, like a fraction. And so if the series terms itself are fractions and I'm using the ratio test, I end up getting a big fraction with little fractions in it. So once you've done this a couple of times, you can simplify this pretty quickly. And a lot of times people will even skip this first step that I've drawn here because it looks overly complicated. But instead, what we'll do, instead of taking one fraction divided by another fraction, we'll take the bottom fraction that you're dividing by and flip it and multiply. So if I write it that way, it looks better pretty quickly. So this is the limit as k goes to infinity of 10 to the k plus 1 divided by k plus 1 factorial times the reciprocal of the bottom, which would put the k factorial in the top, and then put 10 to the k in the bottom. Any questions about how I did that first step? Okay, so now we would say, how can I simplify this? So first of all, the exponent part here, the exponent part can be simplified because we have a property of exponents that if I have the same base in the top and the bottom, then when I divide, I can just subtract. So 10 to the k plus 1 divided by 10 to the k will just be 10. So basically, this part here would cancel out that complete power there, leaving just 10 to the first power. So I would be evaluating the limit as k tends to infinity. And in the top, I would have this 10 here. Then similarly, if I want to focus on this k factorial divided by k plus 1 factorial, focusing on that part, let me write that off to the side here. If I have k factorial divided by k plus 1 factorial, well, in general, k factorial is k times k minus 1, dot, 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 until we get down to a 1, multiplied together. K plus 1 factorial, instead of starting at k, starts at k plus 1. But then you start counting down from there, so then you'd multiply by k, you'd multiply by k minus 1, and you'd keep going down until you get to a 1. So when you make a fraction out of these factorials, a nice thing happens that everything below k plus 1 just cancels out.
Mr. Willard?
Yes, question.
So I was kind of confused. How did 10 to the power of k cross out k plus 1? I got kind of confused around that.
Okay, absolutely. So let's say we had some number for k. So let's say you had 10, let's say k was 5. So then I would have 10 to the 5th in the bottom, and I'd have 10 to the 5 plus 1 or to the 6th in the bottom. Does that make sense?
Mhm.
So this is if we say k was equal to 5. Then that would be 10 to the 5th in the bottom and 10 to the 6th in the top. Well, basically you have one more power of 10 in the top than in the bottom. So that's 10 to the 6 minus 5, which is 10 to the 1.
So it would be 10 to the power of k plus 1 minus k.
Yeah, which
Oh, I
is
see.
10 to the 1.
Gotcha. I guess the way you crossed it kind of confused me at first. Okay, I got it. Thank you.
Yeah, because they're not in the same fraction there. But yeah, I crossed out the entire thing in the bottom and only crossed out the power in the top, because when I combine them, that wipes out everything except the 1 in the top. Does that make more sense?
Yeah.
Okay, thanks for the clarification. Okay, so what's going on over here with our factorials is that we're left with a 1 in the top and a k plus 1 in the bottom, because all the other stuff cancels out. Maybe I'll also do that with a specific because it's hard to follow. So let's say you had 6 factorial divided by 7 factorial, because it's 1 more in the bottom. Well, in the top, that would be 6 times 5 times 4, down, down, down to a 1. And on the bottom, it would be 7 times 6 times 5 times 4, dot, 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 down to a 1. So everything would cancel out except the 7 in the bottom. So similarly, when we simplify the factorial fractions in these expressions, what we see is that what's in the bottom is just k plus 1 is left. So what cancels is that the k factorial cancels out the factorial part of k plus 1, just leaving k plus 1. So we're left with the limit as k tends to infinity of 10 over k plus 1. So now the only k that's left is in the bottom, causing the denominator to head off toward infinity, while the top just sits there as a 10, 10 over 100, 10 over 1,000, 10 over a million, 10 over a billion. So this limit is 0. So we were setting this limit up.
Quick question.
Yeah.
Can we also take the 10 out? And so it'd be 1 over k plus 1.
Sure. But 10 times 0 is still 0.
Right.
But yes, you can actually, absolutely, you could take the 10 out. Yeah, that's a manipulation that we have. In fact, that's one of our limit of a convergent series properties that we were just looking at, right? Okay, so what were we doing here? We were calculating a limit, which this number r, of this ratio of successive terms. And based on the value we get from that, we're supposed to be able to draw a conclusion about being able to converge or diverge using the ratio test. So if r is equal to 0, what does the test tell us we should conclude? You guys see it?
The series converges.
So yeah, we have this situation going on here. And it says if r is between 0 and 1, including a 0, then the series converges, and r came out to be 0, so it converges. So even though the first few terms kind of make it look like it's getting bigger and bigger, the reality is that this is convergent. And that's something to think about, because I'm also hoping that as we do more of these problems, you'll work to try to develop an intuition about what's going on a little bit. And so normally if I had a fraction where the numerator was created with terms that are experiencing exponential growth and heading off to infinity as powers of 10, that you think, wow, that's going to be runaway growth like exponential functions, which is way faster than polynomials or anything else. But is now something which we can recognize as being faster growth than exponential growth, and that's factorial growth. Because these terms were getting larger, but they would only do that up until you got to the 10th term. Because after the 10th term, as k goes up in the factorial, you're taking what you had before and multiplying it by a new number that's bigger than 10, like 11, 12, 13, 14. Whereas on the top, as k continues to go up, you just keep multiplying by another 10. So the terms of the series as you go out there, you end up taking the previous term and multiplying by 10 on the top, but multiplying by something bigger than 10 on the bottom. And eventually you're multiplying by the next term, you multiply by 10 on the top and 1,000 on the bottom. And the next one you multiply by 10 on the top and 1,000,000 on the bottom or something. So it ends up that the k to the factorial, the k factorial, ends up growing much more aggressively than 10 to the k and causes the whole fraction to shrink away down to 0. And it causes this limit to converge very aggressively because the range of the ratio values that lead to convergence are anywhere between 0 and 1. And this is all the way down at a 0. So that means this converges very aggressively. And we'll learn more about what that means in chapter 9. But for now, the ratio test gave us a way to look at this series. And our previous tests had no way to handle it because we had no way to deal with the k factorial because it's not a function. And it gave us a test that we could use to see, yes, this does converge. As with all of these, it doesn't tell us to what value it converges, but we do know that it converges to some number. So I could then sort of, ideally, I'd finish this off by saying something like therefore with the 3 little dots, or thus, or the series converges by the ratio test. And again, to be clear, your ratio test is going to be one of your most important, most frequently used tests. So you will get used to it pretty quickly. You'll want to use it a lot. It is often gives you the clarity you need in challenging problems. And so it's a very, very good test to start with in 8.5. Questions at all about the ratio test or this example that we used for looking at it?
Yeah, Professor, I had a question. So, how did we get to? I'm a little bit. I get the simplification part, but how we got our R is what I'm a little bit confused on. From what Siri gave it, from what was given to our R value.
Well, R is equal to this limit. And so as I was simplifying the stuff on the right so that I could apply the limit, right? So I started by trying to take the limit of this ugly thing. And then I simplified that to here. And then we were able to cancel out a lot of stuff. And we ended up just taking the limit of 10 over k plus 1.
Yeah,
so
and
that
part.
reduced to 0, and that's R. R is whatever that limit is.
Yeah, but when we originally set it up, so how did we set it up? So like we had 10 to the k plus 1 over k plus 1 factorial.
I see.
So
Where did that come from?
Yeah, where did that part come from? How we set it up?
Okay, so we were given this formula for a sub k, right?
Right.
So the way you set up the limit for R, as it says in the theorem, is you make a fraction where you put your original series term in the bottom of the fraction. And in the top of the fraction, you take the same series term, but instead of doing the kth term, you do the k plus 1 term. And what that means is that everywhere there's a k, you plug in k plus 1 instead.
Okay.
So this here is k plus 1 instead of k in the original series. So instead of 10 to the k, we did 10 to the k plus 1. And then in the denominator, instead of dividing by k factorial, I divided by k plus 1 factorial. So you swap out the k's in the formula with k plus 1 instead.
Okay, so for the numerator, it'll be k plus 1 for whatever we have. And then at the bottom, we keep the same what was given, right?
That's right. So take a look at the presentation of that theorem here. Here's what was given. Notice that that's what's in the bottom. And then in the top, the only difference is instead of k, you have k plus 1. Does that make sense?
Yeah, that makes sense.
So why don't we just try taking another example where all we do is set up the limit and then we don't worry about doing it because we need to move on. So consider a follow-up example, and I'm just going to say set up the R value. So we have a series, and I'm going to look at maybe their B in the same example, which was, this will be fun, k to the k divided by k factorial. So for the ratio test, we let R equal, actually I'm going to run out of space there. I'm going to let R equal the limit as k goes to infinity. So basically when you, as I was saying before, if your terms are a ratio, then for the ratio test, you're going to have a fraction of fractions. And so it's probably better to take the fraction on the bottom and flip it. So I'm going to have a part here for k plus 1. And I'm going to have a part here for k, but that I flip. So the part for k, because I'm changing to multiplication, is the fraction I just had. So I would put the k factorial in the top and the k to the k in the bottom. Because I'm supposed to divide by that fraction, so instead I multiply by the flip of that fraction. How do you feel about that part? So for the k plus 1, I make the same fraction and I replace every k with a k plus 1. So over this one, I would do k plus 1 to the k plus 1. And then on the bottom, I would do k plus 1 factorial. Then I would have to, then I'd be trying to evaluate this limit to determine my R value. Questions about that setup for the R value? So I'm going to feel okay to not do the rest of the problem because this is an example that they do for you in the book on page 641. So they'll go ahead and do the rest of it for you. But when you're getting used to using the ratio test, the first stage is to get a sense of how you set up the limit that you need to evaluate to get the R value for the ratio test. So questions about that setup at all? Okay. So I'm now going to get rid of all this so we can look at our next test. So then on the bottom of page 642, we're going to have Theorem 815, which is the root test. So let's write it down, try to understand what it says, and then look at an example of how to use it. So again, let's say we have some series of a sub k's. It's an infinite series. And again, it's going to be non-negative terms. Typically positive. So then we're going to do another limit. So the letter they use for the limit is a rho symbol. So basically looks like that. Kind of looks like a small italic P. Looks probably more like that in the book. But anyway, it's a Greek letter rho. So we're going to let this equal, it's kind of like the R we did before. This equal the limit as k tends to infinity. So what is it? We're not going to have a ratio this time. It's a root test, so we're going to have a root. And our root is going to be the kth root of a to the k. So it may sound disastrous to add a root onto something when we're trying to take a limit, because limits of root problems are not usually friendly, but we'll examine that in a minute. So let's say we take this limit and we get a number, and then it's going to basically have the exact same three criteria that the ratio test had. So this hopefully will be easier to remember. So if 0 is less than or equal to this row number, which is less than 1, then the series converges. And if this row is greater than 1, and that even could be that you get a limit that goes to infinity, then the series diverges. And if rho comes out equal to 1, then, like before, the test is inconclusive. Hey, honey. Sorry, guys, just a sec. So why don't you try to do the Zoom on your phone or something to try to go into that meeting for Kids Club? I'll be done here at about 3:15. I can help you after that, okay? All right, sorry, guys. Kids are at home. So this ends up being, oh yeah, you're right. Thank you, Wenzel. Thanks for the correction. Yes, that's supposed to be greater than 1, so let me fix that. Appreciate that. Yeah, so this basically has the same criteria that we used in the ratio test, but now it's in this root test. And so instead of using an R for a ratio, we're using this rho symbol, and we're taking the limit of a root. So how is it that sticking a square root on something could make our life easier when we're trying to apply a test? Well, basically that's going to happen when the thing that you're square rooting, or I shouldn't say square rooting, that you're kth rooting, that you're taking the kth root of, is it already has a power of k on it. So if the a sub k term is something that has a kth power, then when I take the kth root of something with a kth power, they would cancel out. It's not square root of a raised to the power of k, because if I don't know what a is if it doesn't have a k subscript on it. Like a is different for every subscript. But let's look at an example, because the notation is definitely making this challenging. I'm just going to make up my own to keep it real simple. So consider the series as k goes from 1 to infinity of, I don't know, how about, let's try this. 9/10 plus 1 over k, all raised to the power of k. So what does this look like? Well, when k is a 1, we have 9/10 plus 1, because 1 over 1 is 1. So that would be 19/10 raised to the power of 1, which is 19/10. When k is a 2, we have 9/10 plus 1/2. 1/2 is 5/10, so that would be 14/10, then raised to the power of 2, so that would be squared, etc. So this is kind of an ugly looking thing. However, it's going up to a power that's higher and higher each time, and then inside you have a number that's basically, as k goes to infinity, this part is shrinking away. 1 over k is kind of going to 0. So we kind of like to think that this is like 9/10 to the k, because this part ends up becoming insignificant. And 9/10 to the k, well, that's a geometric sequence. So that's going to be something that you might think converges. Anyway, you might be able to get some intuition about it. Certainly no one at this point I would expect that of, because you're just getting introduced to all this stuff. I don't know, straight after this later. So, so we would say, all right, well, there is this power on here. So the thing that makes you think you want to use the root test is the fact that you have this k power on here. So that suggests use root test. Certainly that's what you should try, because that'll make that go away. So in order to do that, I would say, all right, let rho equal the limit as k tends to infinity of the kth root of 9/10 plus 1 over k to the k. So that simplifies nice and quickly. That's why we chose this test, because the kth power and the kth root cancel each other out. And I just have the limit as k goes to infinity of 9/10 plus 1 over k. And then hopefully we may recall that since as k goes to infinity, this fraction drops out, that this just becomes 9/10. So if rho is 9/10, which we can observe is less than 1, then based on the root test, we can conclude that it converges. Because our rho is less than 1. So then we could say, therefore, converges by root test. Questions about that? So yeah, the root test, the root test can be keyed into, oh, hang on a second. It's still too loud, even with the door closed. Okay, I'm back. Sorry about that. So the key for the root test is to note that if I have some series where the terms are raised to the power of k as k gets larger, then the root test will allow me to try to see if it converges or not with an expression where I take the kth root of something to the kth power, and that hopefully leaves me a limit that's much simpler to evaluate. And then based on the criteria of how it compares to a 1, is it less than 1, is it bigger than 1, then I can draw a conclusion. And if it comes out to be equal to 1, then the root test has failed. So questions, comments, discussions about the root test? Okay. So we have another test, but before we get to another test, let's imagine the test that we have at this point, because that's kind of important to the process for this. So we started in 8.4. With the divergence test. And it was a simple test that basically said, if the terms of the series don't go to 0, then it diverges. If they do go to 0, then it is inconclusive. So then we looked at the p-series test. And the p-series test said, well, if you've got a p-series, meaning 1 over k to some p power, then if p is less than or equal to 1, it diverges. If p is greater than 1, then it converges. So then we had, integral test. And that said that if you can do an improper integral of the function that matches your formula for your terms, and the improper integral goes from 1 to infinity, then if the improper integral converges or diverges, so will the series, if you can figure that out. So then we looked at the ratio test, where you take a limit of successive terms as k goes to infinity, let that be r, compare that to being greater than or less than 1. And now we've had the root test, which does a similar thing, but instead of taking a limit of a ratio, you take a limit of the kth root. And so that helps if your terms have a kth power. So we have these sort of 5 tests here. And so the next test is Theorem 816. On page 643. So this is called the comparison test.
Professor, the first 3 are all 8.4, right?
Correct. So divergence, p-series, and integral tests we did in 8.4, and then in 8.5 we've looked at the ratio test and the root test, but they're just piling up on us here. It's always brutal to go over 2 sections in one day. This material just piles up so fast. Okay, so the big thing that I want to think about with the comparison test, when the reason I listed out these tests we had so far, is that the way the comparison test works is you basically have a new series that you're looking at, but you compare it to another series which you could do using one of the previous tests. And so then by comparison, you try to draw a conclusion. So the basic idea is, like if I have a new series and it looks like a series that I know diverges, goes off to infinity, but it's not quite exactly the same, then how can I compare them? Well, if the terms of my new series are each larger than the terms of a known divergent series, well, if I'm adding up terms that are more than a divergent series that goes to infinity, well, then the more terms have to also go to infinity and would have to also diverge. Similarly, if I had a series that I already knew converged and I'm looking at a new series and the terms of my new series are smaller than the series that I know converges, well, then they have to converge as well, because if it's less than something which is known to be finite, it must also be finite. So that's the idea behind the comparison test. Here's how that is written. So again, these are going to have positive terms, but it says let the summation of A sub k's and the summation of B sub k's have non-negative or positive terms. And then it goes through those two comparative possibilities. So the way to state the first one is if the A sub k terms are bigger than 0 because they're positive, and they're always less than or equal to the B terms. And if we know that B sub k is a convergent series, so I know B converges, and I know my new series of A sub k's are the terms are less than the B terms, then the series of the A sub k's must also converge. Basically, if the A's are less than the B's, which are known to converge, then the A's must also converge. And on the other flip side of that, if instead I know that my B terms are all positive, but they're all less than or equal to the A terms, and if in this case my B's diverge, well, then what's going on? My new series of A's are larger than or equal to B's, and B's are already known to go off to infinity or whatever. Well, then how can the A's settle on a value if they're bigger than something that doesn't settle on a value? So then that forces my new series of A sub k's to diverge as well. So that's the statement of the comparison test. So we can look at a simple example of this. Yeah, let's just do one from here. So consider, let's say you're trying to determine the series as k goes from 1 to infinity of 1 over k squared plus 10. So the whole thing about the the comparison test is they're not going to give you both series. They're just going to give you, like every other problem, some series that you're looking at, and you're basically tasked to find out converge or diverge. And you're just looking at it. So the comparison test will feel a lot more useful and make a lot more sense to students, quite frankly, after they've done a bunch of problems with the other 5 tests. Because then you start to accumulate some intuition and some sense of what kind of series converge and what kind of series diverge. Because basically, with the comparison test, you already have to have an opinion in mind, and then you have to come up with a known series that you can compare it to. So here's the kind of thought process. And again, I think you'll be comfortable from this maybe when you finally get there. But here's the idea, that you would look at this and you would say something like, well, this looks like the series of just 1 over k squared. Because again, when k becomes huge, who cares about some plus 10? That's not going to change anything when k is like 1,000,000 and 1,000,000,000 and 1,000,000,000,000. Plus 10 is going to mean nothing to what's going on. So then you'd have to say, well, do I know if the series of 1 over k squared converges or diverges? Anybody have any sense of whether this series converges or diverges? The series 1 over k squared? What do you guys think? Wenzel suggested converges. Anybody else think that's the case? Up arrow, happy smile. I'm sorry, guys. 1 second, I have to take this call. Hello?
Hi, Daddy.
Hey, baby.
Finish your class?
3:15, I'm just trying to finish up now. So you want to call me back in 10 minutes? Is that okay or no?
Yeah.
Okay, call me in 10. Thank
Okay,
you.
okay.
Okay,
Yeah, bye-bye.
bye-bye. Okay. Sorry, just a few time. So yes, correct. Wenzel is correct. This converges, and I would point out that we could say that this converges because of the p-series test, because that's got a value bigger than 2. So I would say it looks like that, which converges. So then the question is, I can just compare it to this convergent series and say that it also converges if the terms of this series are less than the terms of this known convergent series. So then I would say something like, since k squared plus 10 is always bigger than k squared, then 1 over k squared plus 10 is less than 1 over k squared. And the series of 1 over k squared, I said 1 over k squared, 1 over k squared converges by p-series test. Therefore, the series of 1 over k squared plus 10, since the terms are less than that, converges by the comparison test. Questions, comments, discussions about the comparison test? Okay, so those are the main titled tests for this section. And I wanted to also point out that at the end of the section on page 647, so note on page 647 is a big paragraph description for guidelines for choosing a test. So our guidelines for choosing a test. So that'll just help as you get used to these. And again, in the previous section in 6.4, you'll have practice with those other 3 tests. So the big goal for these sections is that you can do C or D problems. You can determine convergent or divergent. For example, in this case, we determined that this was convergent because we compared it to 1 over k squared, which is also convergent, and these are lower numbered terms.